Yeah, really glad to be here. Yeah, really glad to be here, presenting to all of you. I came to the last meeting, invited by Callum actually, and it was really exciting, really interesting. So I'm really glad to be able to present what we've been working on. So we're basically trying to build a company, London Biocompute, and the mission is to create a fully API-driven cloud lab. We're currently working with one of the ARIA-backed teams here in the UK, and they're working on microbial protein biomanufacturing. And so all of the equipment that we've been making so far has been focused around microbial growth experiments, basically. So we're really focusing on having everything be as API driven as possible, trying to provide a much better UX than alternatives out there. So the idea is that it should be as quick to use as possible, just pip install via an API and you can get going. No more 1,000-line scripts or robotics required to do basic things. And we're trying to support multi-step data gathering, search and optimization based experiments right from the beginning, because we see that as an area where people want to do, basically where people want to do a lot of experiments and where AI scientists, such as the people who we're working with here at King's, are going to be basically most useful doing these search experiments. So the approach we've taken to building our equipment and our cloud lab is to be as vertically integrated as possible. So we've tried to internalize all of our critical software and hardware dependencies. So basically building everything from scratch. So we've done liquid handlers, bioreactors, plate readers, scales, peristaltic pumps, and so on. And it's allowing us to basically get started and bootstrap this from basically no money at all, and hopefully will allow us to scale for 100 times less capital. Of course, it also means a huge amount of upfront work and polish required to get to the level where we can run these in a big facility in parallel. But I think we'll get there. We've also done interesting things like building our own sort of CAD framework, hardware description language, and robotic simulation framework for basically making our entire facility simulatable and easily editable, especially with coding agents. So we recently released a GitHub package called Biocompute, and this is like our first attempt at releasing a Cloud Lab style API. And so in this demonstration, I'd like to introduce you to the API and then get your feedback on it, because I think we've made some interesting UX design decisions that I think you all would have really good feedback on. So this is an example of a really basic experiment. So it's literally just doing color mixing, but it demonstrates one of the core UX decisions we've made, which is to completely abstract away any notion of plates, any notion of robotic grippers, or other pieces of equipment, and purely program in terms of individual wells and the conditions you want to set inside those wells. So when you set up an experiment in our domain-specific language, you basically just iterate in Python using a for loop over the number of wells that you want to use in your experiment. And for each well, you apply various conditions. So in this case, you're filling them with different reagents, in this case, dyes, and then applying a measurement operation to the well. And then once this is run, internally, we will actually allocate those operations to plates and decide, hopefully in an intelligent way, how things should be allocated such that you don't have conflicts, such that things that should be incubated, for example, at the same temperature, get put on the same plate. But if you have different temperatures, then you need to split plates, even if you haven't used all of the wells. So there's all of this internal machinery that our compiler does, but hopefully by abstracting all of that away, it makes our API a lot easier and a lot nicer to use. So um, actually, at this point, I will just briefly exit out of the slides, and if I just share this quick start in the chat, if someone feels motivated and has a Python uh, environment open, there's a quick start here, and if you go ahead and run it, I can actually try and run a job live. Um, if you wouldn't mind just only doing like a couple of wells, that would be appreciated. Um, but yeah, if you want to give it a go, you can copy the code. Hopefully, all the login and auth things should be smoothed over. You won't require any API keys. We've disabled anything that would block that, and I will start the worker in the background. Oh, oops. One sec. Oh boy. So I have like a billion Claude code. Okay, okay. Uh,
Is there someone who's happy to run that to give it a shot?
Volunteers?
Sure. What should I do?
So go on the click on the link in the chat, and there's a set of instructions you'll need to install a pip install a package, do biocompute login, put your email address in, and then if you copy this set of like lines of code into a Python file and then submit it using biocompute submit. It's all in the README.
yeah, I linked directly to the quick start. There's basically 3 or 4 instructions. Give it a go. If it can't be done, then we can submit one locally, and I have a stream running that I can that I can show here, which will show the machine actually moving. But while that's going on, I can continue talking a little bit about the compiler because I think you find it interesting. So looking at this example, when you actually execute this, the first thing that happens is the compiler records all the operations. And by operations, I mean things like filling, imaging, incubating, those sorts of things. And then it basically collects those all into a list and then tries to figure out like how to actually assign those to plates. So in our case, we always use 96 well plates. And it tries to be clever, as I said, and take into account things like incubation temperatures and like how to split things and allocate across plates. We then compute a dependency graph. So operations on the same well can be done like one after the other. Um, but certain operations need to wait until other things have happened. Other things can be parallelized. Uh, the compiler is supposed to be smart, as I say, and try and figure out where things can be parallelized or passed off to a different machine or whatever. And then we also do something where in the API, we generally don't refer to specific devices. Instead, we just program in terms of the conditions we want to set, or sort of the abstract capability we want to invoke. And then depending on your overall protocol that gets built up by the end, we then determine which devices it should run on. So we sort of lazily allocate operations to physical devices based on their capabilities. And then, yeah, finally, we do code generation. So we emit an actual executable Python script, which will run. So let me quickly check the command line. Okay. Alan, do you want to try and submit a job as well? Where's my browser?
Okay, that's a better one.
Okay, cool. Okay, so now it's sort of doing the process of compiling and stuff. Okay, and then do you want to move your camera over here so you can see?
Wait, what's happening, Jim?
Yeah, one sec. Oh no,
What?
it got caught there.
Okay, hold on.
Oh, hang on, we might need to rerun that again. Okay,
Do you want me to restart?
yeah, if it's possible to restart.
I'll restart.
So this is the peril of the live demo.
It's incredibly brave.
Okay, so now you can see actually what's running on there. I might have to move over and just hold stuff. You can see there's an absolute nest of wires.
Can people see on my camera?
What robot is this running on?
So this is our own custom machine that we've been making. So this is our liquid handler, all built from scratch. A lot of it is 3D printed.
That's awesome. Is it open source or?
It's not currently open source. We may consider that though. So right now, what it's doing is scanning the base plate. So we use the Raspberry Pi camera on top of the sort of carriage of the machine. And that means that we don't have to spend as much time doing like manual calibrations of like things on the base plate. So you'll see shortly that it will pass by an April tag, if you know about these. They're like mini QR codes that are very common in robotics. So there should be one coming up soon. Yeah, there. So you can see that it sort of detects the April tag, and it will store that position. So it now knows, based on our CAD software, it can then load in a model of that piece of equipment, which is just like a plate holder for the base plate. And it can know then, it can basically derive other positions, like the positions of wells, or at least it should be able to. So now what you're seeing, oh, this one's better. Yeah, you're seeing actual dispensing. Very nice. So we got a bit of blue dye. Yay. So now we have it in kind of a very conservative mode where it will use visual servoing every time to make sure that it dispenses in the correct location.
It was only one well, but now it's imaging.
Yeah. Okay. So is that?
Yeah.
That's it. So that was just a single dispense, and then it imaged the well and sent it back to Callum so that he can use that for whatever he wants to use it for. And so I guess the final thing I'd like to quickly share with you before asking for your feedback and getting your ideas on where we can go from here is we want to start like a media optimization challenge that will run basically completely over the internet. So the idea is we're going to set some kind of metric that you're going to be challenged to optimize for, and we will provide all of the equipment. We'll use all of our incubators, bioreactors, our liquid handlers, and the idea is you can submit like a series of experiments with a budget. So let's say we give you 50 to 100 experiments or so. The goal is to try and search the space of reagents that we have available and conditions we have available, so like different temperatures, and trying to find the sets of conditions that optimize growth for the microbe that we have available, probably E. coli. But if you're interested in doing that, we have a QR code, or you can just go to our website, londonbiocompute.com, and we're hoping to get this up and running as soon as possible. The real thing that's been bottlenecking us has actually been, as someone else mentioned, China going on holiday. So JLC PCB has been very slow to send us various pieces of equipment. But yeah, we're really hoping to get it up and running very soon. And we're excited to see what kinds of strategies people could come up with, especially given the interest in like AI scientists applying like coding agents to optimizing protocols and so on. So yeah, thank you very much for listening.
Thanks. Let's give James a round of applause. Thank you, James. Thank you, Callum. Thank you, robots.
Important to thank the robots.
It is. It is. All right. I'll stop recording and then we can dig into some questions.